Now, in this lecture, students will discuss another type of collinear coordinate, that is spherical polar coordinates. We'll drive the equation for the equation for the gradient called divergence and Laplacian operator in the spherical coordinate. And another collinear coordinate, will compare it with the collinear coordinates. This special type of collinear coordinate with the collinear coordinate, and drive the unit vector in this polar coordinate system, as well as show that these unit vector along the tangential vector in this spherical coordinates are also orthogonal. So let's try a relation between the Cartesian, first relation with the Cartesian and the spherical coordinate of the points. So let's take a point. Let P with the Cartesian coordinate x, y, z be any point in the space. The space x, y, z between the, if this is a point, then we have a three-coordinate axis, Cartesian coordinate system. X axis this, y axis this, z axis. Any point is a position of this point. And let r, theta and phi, r, theta, phi respectively, r denotes the distance of OP. This is the point. Denotes the distance of OP of P from the this position point P from the coordinate system. And the theta is the angle which OP makes with the z-axis. Z-axis is called zenith or azimuth. Zenith angle. OP makes with the z-axis. This is phi. Oh, sorry, theta. And phi with the phi is the angle which the projection of OP in the xy plane makes with the positive direction axis. This is phi. This is zenith, this is azimuthal angle. This zenith angle, or this is azimuthal angle. It's their name, the position point. R theta phi are these are called the spherical coordinates of the point P, and actually the Cartesian coordinate, and that's the spherical coordinates point. Now let's complete the diagram, and after completion, from P drop onto the xy plane. We say xy plane at M. From P, we join the O with O and the put a perpendicular from P on the xy plane, and this is OM. Perpendicular from O on x, this is Q, OQ, and complete parallelogram, and this angle is theta, this angle is theta. Now, now we find the value of the relation between the both the relation Cartesian and this spherical coordinates. So for that, let us consider triangle OMP. MP is a theta, this angle is theta. The parallel line is a parallel line, and this is line, so the angle is equal. Now OM upon OP. Perpendicular, this is theta, this is base, this is perpendicular over hypotenuse, it's called sine theta. Sine theta is equal to OM is equal to R sine theta, and OP, MP. MP is equal to Z, MP upon OP is equal to cos of theta. So Z is equal to, MP is equal to Z is equal to R cos theta. Now again, OP, this OM. Now consider triangle, rectangle triangle OMQ. So this is angle is phi, that is the base, and this is 90 degree. So base upon hypotenuse, is equal to base upon hypotenuse, 20 degree. Is equal to OM upon OQ upon OM is equal to cos of phi. But OM is equal to R sin phi is equal to x become equal to R sin phi cos R sin theta cos phi. Similarly, MQ is equal to R sin phi is equal to y is equal to R sin theta sin phi. So these are the values. These are the relation between Cartesian x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. One here, and z is equal to r. The solution. So how will the r, theta, and phi vary? Because there is spherical coordinates of point P. So they will vary. R increases, R will increase. And this varies from this is 0 to 5, 0 to 5, and this is 0 to 10. So r theta phi is from r is from 0 to infinity, r is from 0 to infinity, theta is from 0 to pi, and this phi is from 0 to 10. Represent any quantum of this space. Any quantum of this space. Any quantum of this space. Now let's find the equations of the surfaces in the spherical coordinates. And the equation of the surfaces which intersect at the point P in the in this is spherical polar coordinates. Square getting for square getting for all these equations x equals to z is equal to this, and this comes out to be r square. This equation is square. Second is square getting first and divided by square of this third. Square getting first and divided by third. This will do tan square theta. So theta comes out to be x y square z square from z square on root of this. That is equal to tan inverse of x y square z square on root of this. And phi is going to divide by waves. This is going to tan phi is equal to tan inverse of y. Now we have got equation for r in terms of z and theta in terms of xyz and phi in terms of xyz. So these are the, if we throw r is equal to c1, theta is equal to c2, and phi is equal to c3. These are the c3. So they will be the surfaces in the spherical coordinate system. This is equal to tan inverse of y next to c1 c3, and is equal to tan inverse of x square plus y square plus z square and root is equal to c2 is equal to c, and is equal to x square plus y square plus z square and root is equal to c1. So these are the surfaces which intersect at the point P in the spherical coordinates. Now again, these surfaces intersect along the curve. Uh, first and second surface intersect at first and second intersecting surface, intersecting curve of first and second surfaces is a U3 curve. Intersecting curve of similar as analogies we have done in the curving coordinates. The the intersecting curve of the second and third surface is U1 curve. U1 curve is uh, UR curve, and phi curve. Technical phi curve is intersecting curve of surface. This is equal to R and theta curve. Theta and phi curve is R1 curve, and phi and R1 curve is surfaces intersecting is theta curve. So these surfaces, this surfaces intersect from the curve. Now we will always find the unit tangential vector to the in the surface in the spherical polar coordinates. Let the unit vector E1, E2, E3 be denoted by the unit vector, unit tangential vector in the curved coordinates. So in the spherical coordinate, they will be denoted by E, R, E, theta, E, phi. Specifically in the spherical coordinates. These vectors act along the respectively in the direction of theta increasing, R increasing, theta increasing, and phi increasing. R increasing, R increasing, theta increasing, theta increasing direction, and phi increasing distance. They at the point, they all act at the point, right? Now, if they increasing in this section, we know then we have now let's find what are the values, what the relation between the these spherical unit vectors and the Cartesian vectors. Now, prove that you have calculated the relation between them. The relation between them. Now we calculate, prove that a spherical four-coordinate system is orthogonal. So for that, again, let's consider the point P. The space with position of is equal to R, which is by x iota plus y z. Now we converted into substitute x y z in terms of the spherical four coordinates. So now push vector in the spherical coordinates of point, spherical polar coordinates of point will be given by is equal to r is equal to r is this. Substitute value r is equal to r cos theta cos phi iota plus r sin theta sin phi j plus r cos theta. Differentiate this to r theta phi. So in order to find the tangential vector in the direction of r increasing, we differentiate the r is to theta. You need to find this is tangent vector in the direction of r increasing. This is the tangent vector. So tangent vector in the direction of theta increasing. This is tangent vector in the direction of phi increasing. Now in front h1, h2, and h3, h1, h2, and h3. Therefore, we know that E1 is equal to S. Therefore, E1 is equal to percentage of R is to R over 2 is to R, H1 upon version, E2 is equal to 1 upon H2. This is a curvilinear, this is the curvilinear coordinates. Then these are tangential to the coordinates. Therefore, yeah, this that we have a special type of coordinates. This is spherical four coordinates. So E1 is equal to E1 is equal to ER vector is equal to 1 upon H1. H1 comes out to be equal to 1. H2 comes out to be R, and H3 comes to R sin theta. Substitute value here. H1 is to 3 and plus R square. Substitute there, and after substitution we got ER vector. E1 is ER vector, E is equal to ER vector, ER E is equal to ER vector. We got the unit vector in the along the tangential vector along the curve. R curve, theta curve, and phi curve. Phi curve. Now we wish to show they are orthogonal. Means when calculated their magnitude, comes out to 0. If we take magnitude of R1, which is R theta, it comes to 1. And E theta, similar as we did in the scale, this is in the report coordinates. Similar fashion, we can find them. And we show that ER dot E theta dot E phi dot phi dot ER, it comes out to be, it comes out to 0. And R ER E cross E theta is equal to phi, E theta E phi is equal to ER, E phi ER is equal to E theta. And ER this, and we show this. ER square is equal to E theta, this comes to 1. Similarly, this ER to ER is the dot product and the dot product. Similarly, ER square and E theta square. Similarly, E theta square, E phi square. Now E theta into phi dot E phi is equal to, and then this comes out to this and this shows alternate spherical coordinate vectors are produced. Now, relation between the spherical basis and Cartesian basis. We have tried the equation relation between the Cartesian vector and spherical vectors. Just like that, we can put this relation between them. We have tried this relation. We have tried Cartesian and curvilinear coordinates, or special type coordinate means spherical coordinates. So from these equations, from these equation, we have written in the matrix form, right? This is the matrix form. This is P, Q, this is P matrix, this is P. So this structure becomes equal to A into P is equal to Q. Now these two vectors are uh, linear independent. Therefore, the determinant of A is not equal to means Jacobian of U1 U E this is to IJ R theta phi not equal to zero. Jacobian is not equal to they are dependent. Result independent they are also dependent. So today you can find inverse here. And inverse multiply by any four sides A into inverse is equal to I into A into P, inverse is Q. So P is equal to N of Q. Find inverse, multiply with superior inverse, you can convert unit spherical vectors into unit Cartesian vectors. With that distribution. With this, you can convert from spherical to Cartesian as well as spherical to Cartesian as well as Cartesian to spherical. Now, if in this equation, drive the equation for the columnar coordinates, you are asked to find the equation of the gradient in spherical coordinates, or in the equation of divergence in spherical coordinate, or the equation of the curve in the spherical coordinate, or the equation of the distribution in the spherical coordinate. You just find the relationship in the Cartesian and spherical coordinates and substitute the value. Substitute the value of B1, B2, E3, E1 is equal to BR, E theta, E5. And substitute them and substitute. Drive equation into the terminal coordinates and substitute their values here, and similarly you can find the equation, this equation for gradient of phi, for direction vector and curl of vector